Hello and welcome. Today I want to show you the spiral of Theodorus. And not only the spiral itself, because the spiral itself is very simple, but in case you don't know it, we will soon take a look at it. So the segmented triangular part of the spiral, with its sharp edges and corners, that is the original spiral of Theodorus. And what you see in pink, the pink continuous curve that's laid onto the spiral, is a continuous extension. And the formula for that extension is something we are going to derive in this video. And trust me, it is going to be extremely interesting how such a simple construct, like the original spiral of Theodorus, can have such a deep connection to all sorts of things. For example, we will encounter the Riemann Zeta function quite a lot of times. And we will do a lot of other very cool things, involving series and involving limits and convergence, and we are going to have a lot of mathematical fun. So let's start by taking a look at the contents of this video. So it will be all about spirals, right? In the beginning, there is the question, what is the spiral anyway? But don't worry, it's very simple, and we will soon be over it. Then we are going to take the original spiral of Theodorus and extend it to an arbitrary segment count. So as you have seen on the previous page, the spiral in its original shape is made out of triangles. And after that, we are going to derive a formula for a continuous curve to give us the nice pink curve that are laid over it. Also, we have to take a look at the Riemann Zeta function and the Hurwitz Zeta function, and a lot of very complicated formulas, but I try to break them up as easy as possible so that you have little to no problem understanding it. But of course, it's going to get more difficult the further the video progresses, so just watch as long as you like and pause if necessary. And finally, we are going to assemble everything, and at the end I'll have wonderful pictures of the final continuous curve. So definitely take a look at that. So let's start with the spiral of Theodorus. So the basic shape the spiral is based on is a triangle. And the triangle in this picture has two sides with the length of 1, and it has a right angle. So it's a right angle triangle, and we can use Pythagoras theorem to just compute the length of the third side, the hypotenuse, I guess it's called. And it is 1 plus 1 squared is of course 1, and the square root of that is the square root of 2. So nothing really exciting here. Well, to construct the spiral of Theodorus, you don't even need to know the Pythagorean theorem. You can just draw this triangle and then continue from that. So let's continue. So what we just did here is add another triangle onto the first triangle. So we used the longer side with length square root of 2. Draw a line with a right angle on its corner. And this line that we draw also has a length of 1. So you already see where this is going. We start off with a triangle with both sides length 1, and on top of the longer side of the triangle we set another triangle also with side length 1, and we can use again, because it's a right angle triangle, and use again the Pythagorean theorem and calculate the next side length, and in this case it's the square root of 3. Why? Well, because we have the square root of 2 squared plus 1 squared is 3. So very, very simple. And now of course we can continue this. Add another triangle, also with a right angle on the hypotenuse of the previous triangle, and we just continue. So you don't need to calculate anything to draw this. You just need to be able to draw straight lines at right angles and always connect the triangles then to the center, so it's very simple. And this gives rise to a spiral. And this spiral that you see here is called the original spiral of Theodorus. Remarkably, that he only drew the spiral to square root of 17 side length. So apparently this is because he did not wanted the lines to intersect each other. Well, you don't have to understand his reasonings, but this is the original spiral. So in a geometric way, we can continue the spiral forever because it's not very difficult to do this. But maybe we want to have the things a little bit more formalized. So let's take a look at a point on the curve. So the point is here in red, and I have this one point here with a pink circle around it. And let's take a bit of a look on the details of this point. So we have two defining factors. So first of all, this point has a distance from the origin, and it's very conveniently given by the side length of the corresponding triangle. In this case, it's the first triangle. And also there's an angle around the origin that gives us the angle of the point. So for the highlighted point, the distance to the origin is of course the hypotenuse of the very first triangle, and that is square root of 2. And the angle of the origin, also very simple, because the first triangle was a right angle triangle with 2 equal sides, so it's 45 degrees on both of the other angles. So we have an angle around the origin of 45 degrees, aka pi divided by 4, and the distance from the origin of square root of 2. So to generalize this a little bit further, we can assign a complex number to every single one of these points. And the complex number is really practical here because they are of the form length or magnitude, which is nothing else than the distance from the origin, times e to the I phi from n. So phi from n gives for the nth point the angle around the origin, and L from n and gives for the nth point the length. So L for length and phi for angle. And n is obviously the corresponding point on the spiral. So I have indicated some points here. Of course, at the very bottom of the first triangle is the 0th point. The point we just looked at previously is the first point. And then there's the second, the third, the fourth, the fifth, and so on. Nothing too special here. And from the Pythagorean theorem, we already know the magnitude, or the distance to the origin, which is equal to the hypotenuse of the nth triangle we drew. And it's a square root of n plus 1. So for the first, for the 0th point, we have just 1, which is square root of 1. For the first point, we have square root of 1 plus 1. For the second point, we have square root of 3 and square root of 4, and so on. So the formula is quite simple. For the angle, things look a little bit different. We already know the angle of the 0th point because it has an angle of 0 around the origin. It lies on the real number line. The corresponding complex number would be 1 plus 0i. So we obviously start right there from then counting our angles upwards. This is just to keep it convenient and nicely in the notation of complex numbers that we start setting the angle of 0 on the x-axis or the real number line. Then for the first point we have 45 degrees, but how does it look for the other one? Well, of course we have the first angle plus the angle inside the second triangle for the second point. So let's take a look at that. The intuition here is very simple. We take the individual triangles, calculate their angle around the origin, and then sum them up for the nth point to get the entire angle around the origin. And here I have a little triangle for you. So we are looking for the angle A, and we know the two lengths L1 and L2, and A just equals the A10, which is the inverse tangent from L1 divided by L2. From the way we construct our triangles, it's very clear that L1 is always 1 and L2 is the square root of n, so the hypotenuse of the previous triangle. So we can say that for the triangle AN, or the nth angle, we have the inverse tangents of 1 divided by square root of n. Very simple. So the inverse tangents of the first angle, which is 1 divided by 1, is obviously 45 degrees, and for the second one we have 1 divided by square root of 2, and then the inverse tangents, and so on. And we get all the angles of the individual triangles, and what's left is just to sum them up for all the different ends. And that's exactly what I showed you here in the table. So now we have two formulas. We have the formula for the distance of our points on the curve to the origin, which is, as I mentioned probably 1,000 times already, the distance to the origin equals the hypotenuse of the respective triangle the point lies on. And that is square root of n plus 1. And additionally, we now have the angle around the origin for the individual point, which is the sum of the angle inside all previous triangles, which we have this little formula down there. So time to take things a little bit further. So I skipped drawing all the triangle lines now, because they just get irritating if you spiral multiple times around, because then these lines get all over the place. I just plotted the spiral itself and the dots on the spiral we get with our formulas that we have derived so far. So the question you see here is, what is about the point 1.5? Well, so now we can essentially assign a complex number to every point that has an integer index. Exactly with these two formulas here. So with phi from n we can put in every integer for n, and also in the magnitude we can put in every integer, and then we can have this spiral with integer points, integer spaced points on it as long as we want. So we are not limited to the first 17 like Theodorus, and we are also not limited to drawing it with triangles and right angles anymore. We have a formula that precisely determines the position of each of the points. So that's already quite nice to have. And we can continue this as long as we want. But the problem is that between 2 points, let's say the first and the second point, like where the pink arrow indicates, we don't know how the spiral looks in between. So what I did here is just draw a line in between these points to somehow approximate the spiral. But to be honest, this is really not looking like something true underlying principle that's inside here. That's just a random interpolation. And for those of you who already had the same idea as I did at this point, why is the following formula that we're going to derive better than a random interpolation? Somehow this question came up in my video about the gamma function already, and indeed a lot of things here are highly connected to the gamma function. So if you watch this video about the gamma function, you might find some principles and problems and general connections in this video as well. So maybe you want to watch it. But don't get stuck here. So if we want to have our data for the point p 1.5, so n is then 1.5, the magnitude or the distance from the origin of the point is no problem. We can just put 1.5 into n for the square root of n plus 1 and we get the square root of 2.5. So no big problem there. We don't have to change anything for that formula. It's already working well on numbers that are non-integers. But the angle, it's a totally different story because we are summing up to n. And if n is not an integer, there is not really a definition on how to sum to n. So we have to try to reformulate this formula using identities and find a different notation that allows us to put in a number that is a non-integer, a fractional, for example 1.5. So let's fasten your mathematical seatbelts, because now we are going to start off. And we start by dismantling the sum. So we already know phi from n, and we have the sum over the inverse tangents of 1 divided by square root of m. So the first thing we have to check is that 1 divided by square root of n is smaller than 1. And that is relatively simple, because of course for all m larger or equal than 1, so everything we can find inside of our sum, the whole fraction will be smaller than 1. So after we have checked this, we can replace the inverse tangents of x using the following sum identity. So we have the infinite sum, it's an alternating sum, and it's going over x to the 2k plus 1 divided by 2k plus 1. And the important thing is, this sum is only valid if x is smaller or equal than 1. And guess what? We're going to plug in 1 over the square root of m for x. Exactly like here, marked in blue. And we can do that because the condition that x is smaller or equal than 1 is still fulfilled. So we can reformulate the whole formula as shown here. And we still sum to n, and we have now another sum inside, but the inverse tangents is gone. So that's already a very nice first change to our formula. But how can we use that? Now we are going to rearrange the sum. So the first thing I'm going to do is take the things that are independent of m and draw them out. And then I can take the sum over m to n and put it inside. So what we do here is we flip the summation signs and then we draw out everything that is independent, because it's a constant factor and a constant factor can be pulled out of the sum. And the final thing I'm going to do is merge the exponents with the exponents of the square root. So 1 to something, everything is always 1, and we can combine it nicely with the square root so that we have m to the power of k plus 1/2. So our sum over n got remarkably simple by now. We have no inverse trigonometric function, nothing too special here. We have just the sum from m equals 1 to n over 1 over m to some power. And this is part of the harmonic series. We have touched the harmonic series already in the video about the gamma function. And the definition is as follows. The harmonic number Hn generalized to the power k plus 1/2 equals exactly the sum we actually want to solve. So this definition alone doesn't take us any further. We want to find an alternate representation of the harmonic number that allows us to switch out n for a fractional number without having problems like in a sum where you can't really sum to a fractional index. That's not working. But before we are going to do this, we have to look a little bit at convergence. So if k is larger than 0, k plus 1/2 is also larger than 1, and then the infinite harmonic number equals, of course, the sum to infinity, and this equals the Riemann zeta function. So here the zeta function comes into play. So the thing is, the zeta function given an arbitrary argument does only converge if the argument of the zeta function is larger than 1. And in our case, the argument is k plus 1/2. So if k plus 1/2 is larger than 1, then the zeta function, and therefore the infinite sum over the inverse powers, will converge. The thing is, it's only true for k larger than 0. But given the initial definition, k can also be 0. So we have to do a case separation later. One case k equals 0, one case k larger 0. So for the beginning we look at the case k larger 0. And then we also get a very nice convergence. So now there's a brilliant idea. Let's take a look at the following sum. So I just plugged in values for n so that n equals 2. This is very simple. Then we have 1 divided by 1 to the power of k plus 1/2 and 1 divided by 2 to the power of k plus 1/2. Is there any different way we can write this, given the fact that for n going to infinity, the sum converges? And yes, there is. So first of all, we just sum to infinity. So we start 1 over 1 to the k plus 1/2, 1 over 2 to the k plus 1/2, and so on to 1 over infinity to the k plus 1/2. Whether this notation is especially useful or if it makes any sense, I don't know. But I think you get what I mean here. We can do this because this will converge to a finite number. And at the same time, we subtract from that finite number, the convergence in the limit to infinity, a second series, but this time we start at 3. And we do exactly the same. So we start by 1 over 3 to the power of k plus 1/2 and so on and go to infinity. And the difference of both of them, I mean it's very clear here, is of course our sum to n equals 2. So how can we leverage this? Back to the harmonic series. So this is exactly what we did the moment before. Instead of summing to n, we can also sum to infinity if the sum converges to a finite number, and then subtract a second sum that starts at n plus 1 and goes to infinity. This is really easy to reformulate. I mean, if we start at n plus 1, we can also start at 1 and just add n to the iterated variable inside the sum. So if we have m plus n, or if we start with m at n plus 1, it's basically the same. We just swapped indices. But this does mean a lot. Well, in particular in this case, it means that now we can plug in any number we want for n, and we don't have the definition problem. So you see on the left side, if I take for example n equals 5.7, the sum to 5.7 isn't really defined and we don't know really how to do it. But here it's very clear. Both go to infinity, both start at 1, very easily, and the only thing in the latter sum, so in the second one, we take n and we add always 5.7 to m, and then take it to the power and everything. So now we have reformulated the original sum in such a clever way that we can extend it to fractional arguments, real arguments, and probably even beyond that, without any difficulties. So I think this is very remarkable how smoothly this went. Of course, we can simplify this notation by using the definition of the zeta function I introduced earlier. But this is just a change in notation. There is nothing special going on in this step. So as I already said, n can now be set to an arbitrary number. And this is of course only true if the infinite series converges. So back to the angles. Back to our original sum. Let's get it as a reminder. So after splitting the sum and rearranging it, we got the following infinite sum, and I'm using the short notation of the harmonic number instead of the sum to n here. For phi from n, which is our angle around the origin for the nth point. Remember, we want to plot in values like 1.5 to get a full continuous spiral instead of this line segments, discrete points that we don't really know what's in between them. And what we have to do now is split the sum. So you see we start at k equals 0, but we know that for k equals 0, our formula doesn't work, because the corresponding series, or the zeta function, doesn't converge. So we are simply going to take the case k equals 0 away, just split the sum at this point, and have the remaining sum start at 1, and for 1 and onwards, our formula we discovered on the previous slide will easily work. So let's insert it. So that is our current progress. So we can calculate phi from n really easily, and the only thing that's still giving us problem is the harmonic number of the power 1/2. So for that special case, we now have to take a more detailed look. The entire rest of the formula is perfectly suited for calculating our fractional points and every other irrational points, transcendental points on the curve. We can plot in any value there, put in any value we want. So let's take a look at the special case. What about the harmonic number generalized to the power 1/2 or 1/2 up to n? So the sum is very simple here, and it's not a big deal that this diverges. There are a lot of proofs out there, but I don't really bother in proving this here. As a little hint maybe, we already know that the harmonic series, which would be m to the power of 1 instead of 1/2, also diverges. And then it's basically clear that this one has to diverge as well. But even more interesting than this is that even the pairwise difference diverges. So take a look at the following. We don't even have to sum up both of the series, so the original one of m to the power of 1/2, and then the second one, the shifted one. So I hope you remember it. Shifted one, m plus n, so we started later in our summation. So we don't have to sum them up both separately and then take the difference. We also can take the difference while summating. So we can take the pairwise difference. This can reshape itself very nicely, and indeed it makes the convergence a little bit better, because our exponent is no longer 1/2, because after we take the pairwise differences, our exponent is now around 1. So you see we have on the very right side m squared plus m times n to the power of 1/2. So let's just ignore the m times n for the moment. So we get to around 1 divided by m if we take the square root of m squared. This would then be exactly the harmonic series. Unfortunately, and this is really unfortunate, the harmonic series diverges as well. And it is the last series in terms of these powers that diverges. So if our exponent wouldn't be 1/2, but let's say 1/2 plus 0.001, we would get a convergent series in the pairwise difference. Very simple, for example, the harmonic series in the pairwise difference will go to a quadratic series. So if you just cancel out all the 1/2s in the final row here, then you will see what you get if you take the pairwise difference of the harmonic series. And this will result in a quadratic series, which is converging very nicely. Unfortunately though, 1/2 is the very last case. So everything larger than 1/2, like 3/3 or 2/3, it will always converge. But here the pairwise difference does not work as well, which is very sad, because it would be a very neat way to extend our formula in a very simple way. But unfortunately the simple way is blocked here, so the spiral doesn't want us to go that simple. It does not want us to get away with that. So we need a different approach. And I can already warn you, unfortunately, this approach is going to get very ugly. So again, back to the special case, we want to sum to n over 1 divided by m to the power of 1/2. So nothing changed here. So our original approach, like we did for everything larger than 1/2, was to take the infinite series of 1 divided by m to 1/2, or k plus 1/2, and then subtract the infinite series that started later in summation, and in fact precisely n summons later. And we can still plot in fractional parts here, however both of these series won't converge, and the pairwise difference won't converge as well. But maybe the underlying identity of difference will still work and we can reshape it. So let's just try this. Assume the difference equation holds, but the sum define formulas that need an analytic continuation to 1/2. So it's about the same as with the Riemann zeta function. You probably already know it, that there is a sum for the zeta function. In fact, the sum we have here, where we plotted in 1/2, is actually the sum from the Riemann zeta function outside its realm of definition. So by using the analytic continuation of the zeta function, we might get still something that we can use. I'm not going to bother you deriving the full analytic continuation, but we're going to take out a little bits and pieces here and there. I thought they were interesting to show, and they were quick enough to show off in the video. So for example, this guy here. We just plotted in the different definitions that we are now going to use the zeta function and its analytic continuous, instead of still sticking to the sum definition that is obviously divergent and does not define the zeta function properly for the value of 1/2. So let's just take a look at the left expression at zeta from 1/2. We're going to try to find something for zeta from 1/2. The thing on the right is called the Hurwitz zeta function. I'll just briefly cover it later because it's way too complicated to show off in a video or as a sub chapter of a video. So let's just stay with zeta from 1/2 and derive it. So we come to the zeta values. Interesting, right? We started off a spiral constructed from triangles, and now we're deep inside the zeta function and we are working around and with all the series and power stuff. It's quite interesting how quickly things can escalate in math. So of course we know it's divergent, the sum doesn't define the zeta function here, but let's take a look at this different sum. You see, it starts also at 1, goes to infinity, and has the same terms that is summed over, but the sum is alternating. So we have -1 to the power of m minus 1, and it's always flipping. 1, minus 1, 1, minus 1, and you see it on the right. Nothing too special, except that this sum is convergent. And this sum also defines a function, which is called the eta function. Very, very, very creative naming. And we just denote this as eta from 1/2. And if you implement the sum in a computer, you will get a finite value in the end. So we kind of can use the eta function to calculate and maybe derive a value for the zeta function, or to analytically continue it somehow. So here we just have again the first terms of the sum that defines the eta function. And in orange I have highlighted here some terms that are especially interesting, because under the square root there is always a multiple of 2. And as we know, we can pull the 2 out. So for example, 2 is 2 times 1, and 4 is 2 times 2, and 3 would be 2 times 3, and so on. And because we are under a root, we can pull this out to be the square root of 2 times the square root of 1, square root of 2 times square root of 2, square root of 2 times square root of 3, and so on. So let's briefly think of this and add another series down below. So if we take the top series and we add 2 times the square 2 over the square root of 2, 2 over the square root of 4, and so on, 2 over the square root of all even numbers, then the top series will be equal to the zeta function. To the zeta function pseudo sum definition of 1/2. And what we have at the bottom is exactly 2 times the square root of 2 times the zeta function from the same thing. So let's combine this into an equation. So we know that the eta function equals the zeta function from 1/2 minus square root of 2 times the zeta function from 1/2. And now we can reformulate this to having the zeta function from 1/2 equaling the eta function from 1/2 divided by 1 minus square root of 2 by simple reshaping of the equation. And this is something very interesting, because the eta function in its sum definition is convergent, and of course we can always compute it and then divide it by 1 minus the square root of 2. And this analytically continuates somehow our zeta function, which had a divergent series before. Quite nice, actually. So that's the easy part. Let's take this knowledge and keep it in the mind. So the Hurwitz zeta function, what you see here with 2 arguments, is something I'm not going to cover in this video. It's just not so easy. And unfortunately, there's also no short and easy way to completely solve the harmonic number to the power of 1/2 and the index n, because the Hurwitz zeta function is just out of scope. So this was our previous approach, and we found something for the first term, and we just leave the Hilbert zeta function as it is. So on the right side, just as a little reminder, the definition of the eta function as a sum, and of course, you know, on the left side we just leave it now as it is. But for those of you who want to know how I actually computed the Hilbert zeta function, without further explanation, proofs or anything, a very complex formula. So the formula you see here has been discovered by mathematician Helmut Hasse, and it was around the 1930s. So you can look it up on Wikipedia, you will find it there, and it works like a charm. But deriving it is something too long for this video. Because now I finally want to come to a conclusion. So what we did, we have now the phi from n formula as we derived it, with the special case shown here below, and the Hilbert zeta function and the sum I gave you just on the previous slide, the formula how to calculate it. Just take it as a given, we didn't derive that, but I mean, I know it's a pity, I always want to derive everything I use, but this is just out of the scope. So except for the Hilbert zeta function, in our 1/2 special case, everything else was neatly derived, and it easily stacks on top of each other. Of course, we still have the function for the length, L of n equals square root of n plus 1, and we now can finally put together our point, which is given as a complex number, L from n times e to the power I phi from n, with phi given above and L of course given above. So, just onto the little bit question, why is this continuation better than linear interpolation or spline interpolation or just drawing any random line that connects the points? Well, this is also a very deeply topic, which I think there is not too much research at all. Maybe there is and I just don't know. But we derive the above formula mostly using identities. And using identities means that we don't add information and we don't remove information. Things that interpolations, regressions or any other sorts of drawing a line between points usually do. So we use the extra information we had for these points, which was given in terms of a sum formula for the discrete points. And then we reshaped it using identities to kind of get the underlying continuous system. And you will find this in many more places, like the gamma function, where I already kind of worked out basically the same. So the factorials are also given only at integers. And there are not too many ways you can meaningfully continue between the integers to get the gamma function. So there's a huge gap between a random interpolation or just applying any common interpolation method, and which you could do to any sort of set of points. So I can give you a random set of points and you can interpolate them with an interpolation method, but giving a set of points of the spiral, they have a predefined underlying sum or formula that define how these discrete points are arranged. And by reshaping this formula using identities, you get an underlying continuous system that is more or less unique. So there might be multiple, maybe even infinite many, but they are certainly more unique than just randomly connecting the dots. But now I have probably talked enough, and let's take a look at the spiral. So here we start, and we go on further and further. So I have to say that the spiral looks really, really beautiful. I can take a look at this for quite a while and it's really mesmerizing. Also, it seems to kind of converge into the Archimedean spiral, Archimedean spiral. I'm not quite sure about the pronunciation of his name, but you can just look it up. So, just for the end, I hope you like this math video. For those chemistry people amongst my viewers who watch to this exact point, I want to tell you there will be chemistry as soon as the winter is over, the temperature rises and the weather gets better. Then I'm going to do more chemistry. Promised. Also, there will be a lot more math and generally a lot more videos on this channel, because I kind of feel like doing videos at the moment and I have the time to do them. So, of course, if you did find any mistakes in the things I was doing, reach out to me in the comments or write me a mail. You can do this, and I hope you enjoyed the video. And finally, I have an image for you which shows really in detail how nice our continuous curves extends the points of the underlying triangle spiral we drew in the beginning. Maybe you noticed I got a new microphone and I put a little bit more emphasis on clear speaking. So, given that, goodbye.